Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily LeetCode problem, and the problem's name is kth smallest prime fraction. So you will be given an array which will be sorted, and it will be an integer array containing 1 and some prime numbers, where all the integers of the given array will be unique, and you will be also given another integer which is k. Okay, and for every pair of indices I and j, where I is less than j, okay, uh, and both of the indices lies in the zero based indexing range from 0 to 1 less than array length, we consider the fraction formed by this pair of indices, where the numerator is being formed by the ith index, which is the lesser index, and the denominator is being formed by the larger index, number representing number represented by larger index. Okay, so you have to return the kth smallest fraction uh, that can be formed by picking up these kind of index pairs from the array, and return your answer as an array of integers, where the first entry in your answer array will be the numerator and the second entry will be the denominator. Okay, so let's have a look at the constraints before thinking of an approach. So the given array's length will be of order 10 raised to power 3, and each entry in this array is of order 3 into 10 raised to power 4. Okay, and first number that is in this array of primes will always be 1, and rest of the numbers will be prime numbers. Okay, beyond this number. Okay, and all the numbers of array are unique as previously mentioned in the problem statement also, and the array is sorted in strictly increasing order. I mean, it will be automatically strictly increasing order if the elements are not same, and it is already being mentioned that array will be sorted in increasing order. Okay, so here you can see that sorted integer array. Okay, and then the last constraint is that k, the k that is being asked you, the position of the fraction will be a valid one. Okay, it will not be like that they're asking you to find the kth smallest fraction, and that kth fraction is not even possible in the given array. Okay, so that will not happen, so you need not to place any checks for that. So these are the constraints, and there is a follow-up also for this particular problem, that can you solve this problem in less than order of n square complexity. It means time complexity. So a very intuitive and naive approach that I can think of is, we can just run two loops, one for I and other for j, the first index and second index, and just check all the fractions, possible fractions that can be that we can have, and that will easily solve this particular problem, provided the constraints, because it's 10 raised to power 3, and if you square it, it will be 10 raised to power 6 order of operations, and there is a operation limit. If the number of operations, order of number of operations of your program, that your program is requiring to solve a particular problem, is falling beyond below this limit, then your solution will be accepted. So what is the limit? The limit is of 10 raised to power 8 operations. Okay, so you can call this ops limit, operations limit. So it will be very well accepted, but according to the follow-up, we are being asked that can we do better than n square complexity? Yeah, certainly we can do better than n square complexity. For that, we will use a concept which is binary search. For those of you who are new to this concept of binary search, I will try to find an article on binary search telling you how binary search works, and it how and when to use it. Okay, so in nutshell, what I can tell you is binary search divides your search space into two parts. Okay, and according to some condition, you always eradicate at least half of your search space. Let's say this was your entire search space. Search space is the space or the things that you are searching for. Okay, let's say I was let's say there is one favorite number of mine and I am searching it on number line, and I am going from 0 to, or let's say I have placed some treasure somewhere. Okay, so there is a treasure hidden in a number line, and I have been told that okay, you have to start from the very first index and from the 0th position, or let's say go to till the 100th, and in between or including these two positions you will find treasure somewhere. So one way of doing it is that you will go from 0 to 100. Okay, what binary search does it's somehow by some decision. Okay, you become very sure that at least this half of the this portion of the search space or number line will not contain treasure. Okay, and then your search space then for the next iteration your search space become reduced to this red half only. Okay, then again you do that intuition thing or that decision thing, and then again reduce it to half. Okay, you keep dividing your search space into half based upon some decision, and that's why binary search gives us a complexity of overall, let's say these were n numbers. Okay, so overall time complexity that comes out for binary search is log of n, because each time you are dividing your search space by 2, so time complexity comes out to be order of log n, and this is the thing. Okay, and anyways, I will be providing the link, you can explore it if you are not familiar with binary search. So let's discuss how we can apply binary search here to this specific problem. Okay, for that what I will do is, and to save time also, I will take the code and explain it how we will be using binary search, okay, in this particular problem. So let me take another slide and paste it there. Okay, this is the code. What we are doing is, I think we can zoom it a little bit. Yeah, now it should be visible enough. So each fraction, what we'll be doing is we will be somehow reducing either of the two loops that we are using. Okay, so see, in a n square solution we will be running two loops, two for loops basically. So what we will be doing is, first of all, we will be thinking, okay, if let's say I beforehand know that uh, the fraction kth smallest fraction will not be smaller or greater than this particular boundary, then I will search for only the fractions that will be lesser than or equal to the current fraction. Okay, so for that what we are doing is we are considering the fraction value as our search space. Okay, so fraction value as our search space. Okay, so let's say how fraction values can be there. Fraction value can be from 0 to 1. Okay, 0 in the case your numerator is 0, and whatever may be the denominator, it will not matter, the fraction will become 0. 1 in the case if denominator and numerator both are equal. Okay, so this is the range in which your fraction value will vary. What you will do, uh, you will, just like I told you in the treasure finding thing, you will divide the search space into half, somehow find the middle point here. Okay, so this is your left boundary of search space, and this is your right boundary right now. Okay, these two are the variables that are representing the boundaries of search space. So this is your search space boundaries. Okay, these are the fractions covered. It means that the number of positions that you have covered to find the kth position. Okay, and this is the numerator and denominator that will be in your answer array. Okay, this array I have taken initial values as -1. You can take whatever you want. Okay, and this is just the length of the current array, prime array, that is given to you. So coming back to the search space, so this was your search space. Okay, so once you find the mid fraction value that can be there, let's say I decided to go with 0.5 something. Okay, so what you will be doing is you will be finding, okay, how many number of fraction positions are there that are covered, which are from which are within this range, which are either less than or equal to 0.5. Okay, so you will count all those fraction positions, and then depending upon the number of fraction positions covered, you will make a decision to reduce the search space. Okay, so this is the number of fraction positions covered. If let's say you have covered more than k positions, okay, that would not be the ideal case that you will be wanting for or aiming for. Okay, then in that case what you will do, you will reduce your search space. So let's say we were asked to find the kth uh, fraction, and that kth fraction position was 3. Okay, and by setting our target fraction position, or the max fraction value that we are allowing for searching the positions that we are covering this time, is 0.5. Okay, zero point 0.5 is resulting in covering of 5 positions, but we were aiming for 3. So this is definitely larger than the position that we are searching for. So what we will do next time, this will be your right boundary. Okay, your right search space will be this entire region will be gone. Okay, and your right will be readjusted to this mid value that you have taken. Okay, why we are not eradicating this one also? Because this might be the ideal value. Okay, uh that ideal value of the fraction that we will be, you know, uh taking for the right boundary to. So right boundary will be adjusted. Okay, and then again you will apply the binary search again. Okay, in this reduced range, in this yellow portion. Okay, and things will continue like this. And if it is the other way around, that if there might be a case that the fraction position is either less than, let's say you are covering only 2 positions instead of 5, or even you are covering 3 positions, in that case also you reduce your left boundary. So left will be moved towards here, okay, towards the mid. So these are the two conditions which will be reducing your search space. Okay, in the standard binary search implementation, you might uh, see some implementations where this thing is mid -1. This is dependent upon the problem statement or type of problem that we are facing. So here we want to at least keep the mid fraction value in our search space, reduce search space, because it might be the case that discarding it will, not lead us to the correct answer. So that is why we are keeping it. And now we will talk about what is happening inside this particular loop. Okay, so this particular loop, we are doing nothing but finding the fraction positions covered for this iteration of binary search. Okay, fraction positions covered. So for each iteration of binary search, we are resetting the fraction positions covered to 0 and then calculating how many positions we covered by taking these boundaries. Which boundaries? Left and right boundaries of the search space. And what is the search space? The fraction value, the max fraction value to which we are allowing. Okay, so this is the whole logic. And what we are doing here is, first of all, we are fixing our numerator index on the 0th index. Okay, so this is the 0th index. So first of all, you will fix your numerator index on this. Okay, and then what you will do, you will keep increasing your denominator index. Okay, so why you are increasing your denominator index? We want that the largest fraction uh, that largest fraction in our range should be not bigger than this mid value. Okay, so that's why when we will be moving forward, our denominator will keep on increasing, because we are dealing with a sorted array, and which is sorted in increasing order. Okay, so if your denominator goes up, your overall fraction value get reduced and reduced. Okay, so this is what we are doing here. And then once we stop at a certain point, we will see how many fraction positions, what is the fraction position of the current fraction. Okay, so let's say denominator index stopped somewhere here. Okay, then we will form a fraction from these two numbers. Okay, this will be the numerator and this will be the denominator. Then we will see what is the position of this fraction. Okay, so for the position of this fraction, how we will find out what is the position of this fraction? For that, what we will do, if let's say your denominator index is here and there are some other entries left in the array. Okay, so this is your denominator index. So for all these entries, the denominators will be definitely bigger than this one, because the array is in sorting order. So you can definitely say that these fraction values that will be coming out will be definitely lesser than the current one. Okay, so that's why we are decrementing it from length or total entries that are there. Okay, and then we will be able to find out, okay, how many fraction positions we have covered. Okay, this is the way. And then also what you are doing is, since you are to return the kth smallest fraction, so maximum fraction, if the current value of the fraction is exceeding beyond the maximum fraction value that you have seen till now, then you will definitely update the maximum fraction value first thing. And the second thing that you will be doing is, you will be updating the numerator and denominator. Okay, so why we are taking the maximum fraction value? Because this will ensure that you will you will be covering I mean you will be covering k fractions when you are exiting this loop. Okay, that is for sure. But we need to make sure that these numerator and denominator are also pointing to those numbers which are resulting in that kth fraction. Okay, so for that part we are using this particular section of the code. Okay, and then once you are done with this particular loop, you will be having your numerator and denominator that is required, and you will be simply returning it. I hope I was able to explain it clearly. If you are still having any doubts or any queries in general, then you may ask them in the comment section. And I hope this problem solving session added some value to your DSA journey of owning your DSA skills. And till then, keep practicing and keep solving problems. I will see you in the next video. Thank you for watching. And before ending the video, uh, we would like to mention or discuss upon quickly upon the time complexity. So because of that searching, we were requiring very less search space, you can say. So it was order of from 1 to 0 to 1, how many number, let's say there are x fractions. Okay, so these number of fractions will be definitely lesser than n. So overall it will be log of, let's say from 0 to 1 there are n fraction values, x fraction values possible. So log of x into n. Okay, why n? Because we are running a loop inside our binary search, which is this loop. Okay, this particular loop. So this will be the overall time complexity. Okay, and it will be still lesser than order of n square. Okay, so this is how we will be solving it. Thanks again for watching.